Today we'll talk about non-bipartite matchings. Nice. So last week we talked about bipartite matchings, and the algorithm for finding maximum bipartite matching was pretty simple. We start from the empty matching, and then we add increase the size of the matching one by one. Each time we just run a simple Dfs algorithm to find the augmenting path. Then we find this augmenting path, we increase the size of the matching by one, and so on until we find the maximal matching. Today algorithm will be mostly the same. So we will start from empty matching, and then we'll increase the matching each time by finding some augmenting path. So let's see, what is the augmenting path? Augmenting path looks like this. Again, it's the same thing as last week. We have some path on a odd length. So let's say we have path. Let's say we have 5 edges. So the first and last vertex of the path must be free of the matching. So we have this free node and this free node. And the edges alternate. So the first edge is not used in the matching, second edge is used in the matching. This is not used, this is used. So this is augmenting path. And like in previous lecture, if we find the augmenting path, we can increase the size of the matching just by inversing all edges on this path. So we will take these 3 edges instead. And just increase the size of the matching. So the idea is the same. We start from the anti-matching and then find our augmenting path until we find the maximal matching. The difference is that the algorithm, it's much more difficult to find the augmenting path if the graph is non-bipartite. Just because how we did it in bipartite graphs, we just orient all edges, edges not in the matching, orient from left to right, orient edges from matching from right to left, and then find the augmenting path using some simple DFS. Here we don't have left or right, so we don't have any way to orient the edges such that augmenting path will become some simple path. So now it's a little bit more complicated. Yeah, but the whole idea is the same, and the main theorem is the same. So the matching is maximal if and only if we don't have any augmenting paths. We proved this theorem in the last lecture, so it is the same here. Let's go. Well, again, let's draw some graph. Let's draw some graph. Let's say we have something like, again, something non-bipartite. Let's say we have something like this. And something here, for example. Like this. Yeah. For example, we take this edge and this edge in the matching. And now we have these 2 nodes are free nodes. So when we try to find augmenting path, we may, for example, find this path. So this is the augmenting path. We find this path, increase the matching, and so on. Nice. So let's try to find augmenting path. So how to find augmenting path? Let's try some simple algorithm. What can we do, for example? We can run slightly modified Dfs algorithm. So let's try to modify the Dfs algorithm in such a way that it will only find the augmenting paths. So simple Dfs algorithm find any path. Yeah. So Dfs algorithm doesn't know anything about the matching. Let's try to modify the Dfs algorithm in such a way that it will find only alternating paths. So how to modify algorithm? So more defined DFS. So we'll modify it in a very simple way. So we will take, again, in Dfs algorithm, you have some current node. So let's have node V. We will maintain the current state of the DFS. So we will maintain the state of the previous edge in the path. So if previous edge was the edge from the matching, then we'll try to extend this path by taking some edge which is not in the matching. So we'll try to take all the edges from the matching. Yeah. So if the previous edge we used in the path was the edge from the matching, then we'll try to use the next edge, any edge which is not in the matching. And if the previous edge was not in the matching, then in the next step we'll try to take the edge from the matching. We have only one such edge. So we'll do something like this. Let's see, we have DFS. We'll try V and some state. So we do all the same thing from the DFS. You know how to write DFS, right? And then we say if, let's say, state is 0. So here will be 0, it will be 1. So if state is 0, then we iterate over all edges not in the matching. So we iterate over all edges VU such that it's not in the matching. And run DFS of U and 1. And else, and do something else. I just skip all the parts which are from this simple DFS, right? So you know how to write DFS. I just write the things which are different, yeah? So if the previous edge was in the matching, then the next edge we try to take is not in the matching. And if the previous edge was not in the matching, then we'll take, there's only one edge, yeah? So we take the edge, okay, there's only one edge, VU, which is from the matching. And run DFS from this U and state 0. And so on. Do something else here, do something else here. Do something else is the same as here. So if we found this augmenting path, we want to invert all the edges in this path and so on. Yeah. So I just skip all this part because they're the same like in simple DFS. Yeah. So imagine we do something like this. So we will try to store this state in our DFS so that here we know which edge we actually can take. So this path will be alternating. Yeah. Clear enough? You're supposed to say clear enough every 30 seconds. Okay. What can go wrong? So if we do it like this, what can actually go wrong? If we find augmenting path, so if we start from some node, again, let's write it here. So we start DFS from some empty node, or from some node not in the matching, with state 0. So state is 0, so we go here. The state is 1, we go here. The state is 0, we go here. State is 1, we go here. State is 0. We go here and find the node. Then we find an augmenting path. Yeah. If we found an augmenting path, we just invert this augmenting path and increase size by 1. But what can go wrong? How can it be that there is an augmenting path, but our DFS didn't find this augmenting path? Is it possible? What do you think? Any ideas? What can go wrong in this algorithm? first and last node. No, we don't go to the same node. So we will, again, like in simple DFS, we just mark all the nodes we visit in the DFS, and we never go to the node if we already visited this node in the DFS. Again, I just skip this part here. So the Dfs algorithm is like usual Dfs algorithm. It doesn't try to go to the node if it's already visited. Yeah. So we start from here. We visit this node, mark it as visited, mark it as this, mark it as this, mark it as this. So if we try to go to the first node, it's already visited. So we will not go to the first node. The problem is actually a little bit more sophisticated. No, the problem is we actually changed the Dfs algorithm. So the simple Dfs algorithm just find all the paths. Here it tried to find some alternating paths. So sometimes it may not go to the we separate busy flag for both kinds of states. Yeah, that's a good point. So what could go wrong? We may want to visit the same node twice. So we may go to some node. For example, we may have something like this. Let's have something like this. Yeah, something like this. So if first we go into this branch, so we start from here, visit this node, then go here, visit this node, state is 1, then go here, visit this node, state is 0, then go here, state is 1, go here, state is 0, then go here, state is 1. Now, here state is 1, so we need only, we can only go through the nature which is in the matching. So from here we can go here, yeah? So since we want the path to be alternating, then if we go from this side, then next step we will go here. So we will go from here, we go here. So here the state is 0. And that's all, we didn't reach this node. Problem, yeah? So if we just do it like this, then it's possible that, what's the problem? Problem is we visited this node in the wrong state. So, so this node is visited in state 1 instead of state 0. So to find this path, we need to visit this node in state 0. So we'll go here and find our augmenting path. But we visited this node in the wrong state. So we visited this node, but the state is 1. So we didn't go here. Problem. Yes, we can. You made a good point actually. What we can do? We can do two set of marks. We can mark all the nodes visited in state 0 and mark all the nodes visited in state 1. And here we just say that if we visited in state 0, then we go back. From here we go back, back, back. Now we try to go here and try to visit this node in state 1. Last time we visited this node in state 0, so now we will visit it in state 1. So we'll just say state is 1, then go here, state is 0, then go here, state is 1. And we kind of find this augmenting path. Yeah. But this algorithm will actually not work. Looks simple, but what can go wrong? If you make two marks, so if you mark pairs like vertex and state, what will actually go wrong is that from here, again, when you try depth search, you go here, 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 and from here you will try to go here, because you can. If you go from here to this node, then you go to this node in state 1, then you go to this node in state 0, to this node in state 1, to here to state 0, and to state 1. So the path you found is actually a path like this. So you go here, then you go here, then you go here. Path like this. This is not good augmenting path. You cannot invert this path. It's not simple. So we need this augmenting path to be a simple path. So we can invert this path. If you have the same edge several times in your augmenting path, you cannot invert this edge because it occurs several times in your augmenting path. So having two marks for each node is actually not helping. You still don't know how to find a good augmenting path. Because again, good augmenting path must be a simple path. If you make two set of marks, then you will visit some nodes twice. And when you visit some nodes twice, you have not a simple path. When you have not a simple path, you cannot invert it. So it's not a problem. Okay. So let's go back. Let's go back to this modified DFS. This modified DFS is actually quite important. So let's go back. Let's go back here. Back here. No. Let's see. How can we tell that we actually have this problem in our graph? So, yeah. So let's try to find. So again, you run this DFS on some graph. How can you tell that you actually have some problem finding augmenting path? You have some problem if you try to visit the same node in the different states. Yeah. For example, here. Again, we go here, 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 here. And after this DFS, we will try to go to this node and try to go here in a state 1. So this node is actually visited in two different states. So we know we might have this problem. So there is some node which is maybe visited in two different states. Yeah, it only may happen if you have a node cycle, right? Since this again, so that's why this algorithm is only, this problem can only happen if you have non-bipartite graph. If you have bipartite graph, you don't have this problem because all the cycles have even length. Yeah. So this problem can only happen if you have odd cycle. Okay. So again, this is the only problem which may happen. Good thing. I claim that if this problem didn't happen, then if there is an augmenting path, then we will find this augmenting path. Let's see it more clearly. So, theorem. Small theorem. Let's say this is node V. Very simple theorem. If we didn't find augmenting path, and no node V visited in both states. So we don't have node like this. So let's say this is some kind of problematic node, right? So this node can be visited in two different states. So there may be some problem with this parity, right? Simple theorem. If we didn't find augmenting path in our DFS, and there is no situation like this, then there is no augmenting path. Well, let's prove it. Again, what does it mean if you don't have any node visited in two different states? What does it mean? What your intuition tells you? How the graph looks, where for each node we have some fixed state. So what does it mean? If we don't have any node visited in two different states, it means each node has some state assigned to this node, 0 or 1. So there is some set of nodes visited with state 0 and some another set of nodes visited in state 1. Yeah, we have some kind of bipartite graph. It's not exactly bipartite, but the subgraph visited from these three nodes. So if we look only at the part of the graph which is reachable from these three nodes, so we run DFS from here, so we didn't visit the whole graph. We visited some part of this graph. this part is actually bipartite. Yeah, and we know that in bipartite graph it actually works. So in bipartite graph, if there is an augmenting path, we will find this path. We can prove it simply by induction. So if you have some augmenting path, again, have some augmenting path. So let's say there is some augmenting path in the graph. Let's prove that this DFS will actually find this augmenting path. So we start from this node with state 0. Now, if we start from here, state 0, we will try to take this edge. So we will try to go here with state 1. Since for every node there is only one state, we will go to this node with state 1. Maybe not now, maybe somewhere else, but this node will be visited and the state will be 1, right? So because we can go here, and we know that for each node, it may only be visited in one state. So this node may be visited only in state 1. Now, since we have this edge, we will run DFS from here with state 1. So we will try to take this edge and try to go here with state 0. For each node, there is only one possible state. So we will eventually go to here with state 0, and so on. Eventually, we will go here in state 1, we will go here with state 0, we will go here in state 1. So if you don't have any problematic nodes like this, then if there is augmenting path, you will find this augmenting path. Nice. That's almost all. So now we have three possibilities. Let's write it here. So you run DFS from all three nodes. There are three possible outcomes. First outcome, you found an augmenting path. So if you found an augmenting path, you just increase the matching by 1. Yeah. So you apply this augmenting path, inverse all the edges, and increase the matching. Second case, if we didn't find the augmenting path, no augmenting path, no problematic nodes. Problem. What does it mean? It means there is no augmenting path. If there is no augmenting path, then the matching is maximum. Let's say this matching is maximum. And finally, the third outcome is when we have some problematic edge. Now finally, something interesting will happen in this case. Let's see how the situation actually looks. It looks like this. So we have some problematic node here. If we have some problematic node, it means we have two different paths. So let's say we have node V. This is the starting node. And we have two possible paths. One path of even length. So let's say this path ends with edge from the matching. And another path of odd length, L length. So let's say we have some problematic node here. So there are two different paths. One path has odd length, another path has even length. Let's find the closest node which is common to both this path. So we have something like this. We have some prefix here. We have something like this. Actually, what you need to do is to take one path, then take the second path, and find the closest node from here which belongs to this path. So we'll have picture like this. So, yeah. No, two paths may have different, so we have paths like this. Yeah, so they may intersect in different points. What you do is to find the closest point, common point here, then take only one prefix. So you'll have this pretty picture. Yeah. So let's see what's happening here. What's happening here is we have some augmenting or some alternate path from some free node to this junction point. So we have something like this. Now this edge must be in the matching. Something like this. And here we have two possible edges. So we can go here and have something like this. Or we may go down here and have something like this. Yeah. So that's how the situation looks. So if you have some problematic node here, then you must have situation like this. So you have this common prefix, and then you have two different paths. One path of even length, another path of odd length. What does this actually mean? It means here you have some odd cycle, or the alternated cycle. Yeah. Well, this cycle has no odd length, obviously, and edges are alternated. So this edge is not in the matching, this is in the matching, and so on. Let's remove this V. We don't need this V anymore. Cool. And this is the main structure of this algorithm. This structure is actually called a blossom. Let's write it like this. So this thing is called blossom. These are cool terms. They go from the so the article about this algorithm. This algorithm was written by Jack Edmonds. Jack Edmonds. And the article was called something like Paths, Trees, and Flowers. I just love this name. So it's very poetic. So he just called this structure blossom because it looks like a plant. So here just like the base of this plant, and here we have a blossom. Cool. That's all. So this is the main structure of this algorithm. So what we will do if we find this situation? No, first of all, how to find blossom. So if you find a problematic node, how to find the blossom? No, you can do it. So you can do it like I did here. So you can start from here, find this path, find the common prefix. But actually, it's much more simple. Since you run DFS, and what happens in DFS when you find the cycle in the graph? So if you find the cycle in undirected graph, you always find path like this. So DFS actually works like this. So you go, and eventually you run into one of your ancestors like this. So in DFS algorithm, if you find cycle, you will find cycle like this. It's always happening. Well, since this is just simple non-oriented graph. So it's actually much easier to program as it looks. So when you want to find the blossom, you can do it right in this DFS. So when you find an edge like this, no, it's not a blossom. You need to find, there must be a cycle of odd length. So if you find cycle like this, then you know that here is the blossom. Yeah? So it's actually not that hard to find the blossom when you find the problem. Now, what I want to tell, if you find a problematic node, it's quite easy to find the blossom. So when we will go, your DFS will run like this. You will go actually here, and eventually you will stop in this node, and in this node you will try to go to this node, U, and you will see that node U is already visited but in the wrong state. So you will iterate over all here. You will iterate over all possible nodes edges from the node V, and you will find this edge, and here you will see that node U is already visited but in the wrong state. And now you know you have a blossom, you find this blossom, and so on. So what to do if you find the blossom? Let's see. So you have this blossom. What you do is very simple thing. You will take all the nodes of this blossom and contract them into one single node. So when you find this blossom, you simply remove all the nodes from here and add one single node. So this single node represents this blossom. And these nodes are here as before. It's called a blossom cut. So again, what we do, we contract all this node into one single node. What happens to the edges? So you may have some edges from here. So you may have edges here, here, and so on. You just take all these edges and make them go from this new node. So you take this edge, and now this edge goes from here, and take this edge, and now this edge goes from here. Yes, we can have a nested blossom. So we will continue this process. Yes. So we contract some blossom and then find another blossom which includes this node and contract it again. Yeah. Good. So what will happen after we cut this blossom? We will continue to do the same. So we had graph G, now we have graph G prime, and we'll simply run DFS in this graph G prime. Now, if we find augmenting path in this graph G prime, we can take it, expand the blossom back, and construct the augmenting path for graph G. So, if we find augmenting path in G prime, we can find augmenting path in graph G. Now, how to do it? Let's see. You have some blossom. Okay, let's take this picture. So again, what we just did. So we find this blossom. Contract all these nodes into one single node. Then in this graph G prime, we run the same algorithm. We run the same DFS, trying to find augmenting path. Maybe we'll find another blossom, contract it, and so on. So at some point, we may find augmenting path. Then how to go back from the recursion? So you recursively call the same DFS for this graph, and then if you find DFS, augmenting path here, you want to translate it back to your graph G. So how to do it? No, you found some augmenting path. There are two possible cases. If this augmenting path do not include this node, so you have some augmenting path here. So if you have some augmenting path, this augmenting path do not include this contracted blossom. Then you just translate it to graph G, it is the same path. Yeah. So if you have augmenting path which do not include this new node, let's call it B from blossom. So if your augmenting path in G prime do not contain this node B, then you just translate to a graph G because it is the same path. Yeah, you have all the same nodes, you have all the same path. Now, if you have augmenting path which actually contain this node B. So how does path look like? The augmenting path has alternating edges. Yeah? So this augmenting path must go through this base edge of your blossom. So you must have path like this. So it must go using this node. Well, maybe not from here, maybe it goes from here, something like this. So you start from this node, for example, you go here, then use this blossom, then use one of these outgoing edges and go somewhere here. So what happens if you have augmenting path like this in graph G prime? We want to translate this augmenting path back to graph G. How to do it? No, let's take this blossom. Yeah. Let's again replace this node with this odd cycle. So what we'll have? So we have this part of the augmenting path, something like this. We have this part augmenting path. It's to here and somewhere here. Yeah. Now, what we need to do? We need to connect these two nodes using the edges from this blossom. And I claim we can always do it. No, because what we need to do, we need to find the alternating path between these two nodes, and this path must have an even length, because we start from the edge in the matching and we end with the edge not from the matching. So the number of nodes here must be even. There is always an even alternating path in the blossom. So you can go clockwise or you can go counterclockwise. One of these paths will actually satisfy your conditions, right? Because, well, for example, in this case, you can go clockwise. So if you go from here to here clockwise, so you take this part of the blossom, you will build alternating path from here to here, and this part will also build alternating. So you have a correct augmenting path in G. What the blossom inserted right place in path. Yeah, right. So we go around this cycle, but we need to choose the direction. Yeah. So there are two possible directions. You can go clockwise or counterclockwise. And for this node, you need to go clockwise. But for example, for this node, if you have something going from here, yeah, if you want to go to this node, you must go counterclockwise. But one of these paths will always be correct. Yeah. Because the length of the cycle is odd, so one of these lengths will be even. That's all. So if we find problematic node, we contract blossom, call Dfs in graph G prime, and then how it's called? We'll go to this. Let's transfer this path. Transfer aug path to G. That's the plan. That's all. That's the whole algorithm. Again, let's repeat the whole algorithm again. So what happens? You run this modified Dfs algorithm. So your Dfs algorithm maintains the states for each visited nodes. If you find the node which is visited in two different states, then you found some blossom. You contract this blossom, run Dfs again, then put this blossom back, and just modify your augmenting path so you have our augmenting path in G. If you find the augmenting path, then you just apply this augmenting path and return from your recursion. If you didn't find problematic node and you didn't find any blossoms, it means that your matching is actually maximal. Then just return, and that's all. End of story. Can we miss perfect comparison? That's a very good point. That's a very good point. So, what may be the problem? Problem is we try to contract this blossom, then run the DFS in this modified graph. If we find the augmenting path in this G prime, then we can translate it back to graph G. But what if we didn't find any augmenting path in G prime? What do you think? What does it mean? So if we take some blossom, contract this blossom, then run DFS, and then find out there is no augmenting path in this graph G prime. So again, we run all the same algorithm in this G prime and didn't find anything. What can we say about graph G? What do you think? Okay, what you want to be true? We will prove it, but that yes, the hope is right. That's the right word. So let's hope that if there's no augmenting path at G, then for some reason there is no augmenting path in G. That's actually true. That's a little bit more complicated to prove, but we'll prove it now. Oh, I didn't connect my laptop. Sorry. 1 second. I forgot to connect my laptop. I'm back. Can go on. It's interesting. Oh, let's prove this. No, first of all, this is the only thing we need to prove, right? If we prove this, everything else is cool, right? They may have, the number of different augmenting paths is not a problem. The problem is if we have at least one augmenting path. If we have two different augmenting paths, not a problem. If we didn't find anything here, we want to return from this DFS and say we didn't find anything. Sorry. Yeah. So if we run DFS in G prime and didn't find anything, we want to return from this graph G and say that we didn't find anything in this graph G. That's the only problem we have. Yeah. Let's prove this. Let's draw another picture here. Nice. So we have graph G. Here we have some blossom. Let's do it like this. Small blossom. And we have graph G prime. I will prove this from right to left. I want to prove, so this is the same as, this is augmenting path in G, then there is augmenting path in N, right? So it's the same as right, it's the same condition, right? I just inverse this negation from both parts and reverse the direction of this. Yeah. Yeah. So here's implication from node A to node B. Here's implication from B to A. It's the same. Okay. Now let's go. So I have some augmenting path in G. I want to prove that there is augmenting path in G prime. I will do it in 3 steps. So I will build 2 additional graphs. So first I will build graph H. Graph H will look like this. I will take this. So this node is free. This node is free. So I will take this part, this path, and inverse this path. Everything else will be the same. So I take and just inverse this path. So this edge is used, this edge is used. Yep. Is it clear how I go from this graph to this graph? So I just invert this part of the graph. I can inverse any alternating path starting from the free node. Yeah. So if I have this path, I can inverse it and have this path. This is a correct matching, right? And I'll do the same here. So let's say H prime will be like this. This, and this. Now let's prove. First, if I have augmenting path in G, then I have augmenting path, say P is enough, in H. Let's prove it. So I claim if I have augmenting path in graph G, then I have augmenting path in graph H. How to prove it? Again, let's remember, when we have augmenting path, we have augmenting path if and only if the matching is not maximal. Yeah. So I have augmenting path at G means that M is not maximal. Right? Yes. Now let's say the size of the matching here is the same. Yeah. So when I invert this prefix, I have the matching of the same size. If this matching is not maximal, then this matching is not maximal. Then I have augmenting path here as well. Ta-da! That's all. Now the same thing here. So if I have augmenting path in H prime, then I have augmenting path in G prime. Again, the same logic. These 2 matchings have the same size. So if I have augmenting path here, then this matching is not maximal. If this matching is not maximal, then this matching is not maximal because they have the same size. If the matching is not maximal, then there is some augmenting path. That's all. Okay, now I moved from here to here. and from here to here. Now I only need to move from here to here, right? Now let's prove it. Now I claim that if you have augmenting path in graph H, then you have augmenting path in graph H prime. Okay. How to do it? Let's look at the augmenting path in graph H. If this augmenting path do not include this blossom, so if I have augmenting path like this, then I obviously have the same path in H prime. So if my augmenting path do not contain anything from this blossom, then I have the same path here. If my augmenting path actually touches this blossom, so if it might do it actually quite strangely. So you may have augmenting path which goes something like this. Something like this. So you start from this free node and go here, here, then use this path from your own blossom and then go here, here, here. So you may find augmenting path like this. Now, I claim if you have any augmenting path which includes some nodes from your blossom, then there is augmenting path in graph H prime. Why is it true? No. Let's take this path. So one of the ends of this path is not this base of your blossom. So let's take this base of the blossom. So one of the ends of this path must be different from this node. So for example, this node is different. So let's take this node V and just take the part of this augmenting path from this node V to the closest node which belongs to your blossom. So let's take only this part of the augmenting path. And now translate this part of the path to graph H prime. So in this graph, you will have something like this. Now, since the node B is free, then now you have this small augmenting path from B to this V. That's all. So if you have any augmenting path which includes nodes from your blossom, then you can cut this part of your augmenting path, move it to your graph H prime, and here you will have augmenting path in graph H prime. That's all. So now from this we have this, from this we have this. Now if we have augmenting path in G, then we have augmenting path in H, then we have augmenting path in H prime, then we have augmenting path in G prime. That's all. That's all. That's the whole algorithm. Okay. The proof is, yes, proof looks like kind of magic, but it's the easiest proof I know for this theorem. You may prove it. You may use something like dual problem to prove it, like from other side, but I believe this is the easiest proof. And it's very visual and it's very simple. The problem is that if you want to make a constructive proof, if you want to construct from this augmenting path, that might be complicated, because the path may look completely different. Because then you can, again, like here, when I contract this path, I have this long augmenting path, now I have this short augmenting path. This long augmenting path will no longer be augmenting path, because here, if you just take this augmenting path, then here you will have two edges. These two edges not alternate. So you cannot just contract the blossom and take the same augmenting path and say this augmenting path will be again augmenting path. That's not true. So proof is a little bit sophisticated, but good enough. So again, how the algorithm works. So you start from graph G. Yeah? You run DFS. If your DFS find the blossom, then you contract this blossom. You get graph G, G prime. Run the same DFS in graph G prime. Find another blossom, contract it again. Take graph G prime, and so on. At some point, you will find augmenting path. You have two options. If you run the algorithm and didn't find any blossom and didn't find any augmenting path, it means that your matching is actually maximal possible. So you cannot find augmenting path and you didn't find any blossom. It means there is no augmenting path, so your matching is maximal possible. If you found augmenting path, then you translate it back to graph G prime, and then translate back to graph G. Then you apply this augmenting path, increase the size of the matching. So you increase the size of the matching. And then do the same thing again. So again, you start from graph G, try to find another augmenting path. You find blossom, find blossom, find blossom, then go back, 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 apply augmenting path, increase the size of the matching, and so on. Now, all these actions can be made in linear time. So you can run DFS, find the blossom, contract the blossom, expand the blossom back, and so on. So all this operation can be done in linear time. Maybe some of these operations are a little bit more complicated, but you can do it as an exercise. So all these operations, like contract the blossom, expand the blossom back, transfer the augmenting path back to graph G, and so on. All these operations can be done in linear time. You can think about it if it's not very clear. So you spend m time, let's say m is the number of edges. M here, m here. So all these operations take linear time. So what is the total number of these operations? So how many times should we run this DFS until we finally find the maximal possible matchings? So let's see. When we increase the matching, we cannot do it more than n times. Yeah. So when you increase the matching, you cannot do it more than n times. No, n over 2 actually. Yeah. Well, because you have only n nodes, so the total number of edges in your matching cannot be n over 2, right? Now, what about these contractions? How many times can you contract a blossom until you finally reach the bottom point? So you will find the augmenting path or you will stop. What is the maximal number of iterations here? Why this algorithm is actually terminated at some point? Why it's not? Why can you do it infinitely? Why can't you contract the blossoms infinitely? Yeah, every time you contract some blossom, you decrease the number of nodes. Yeah, so the number of times you decrease the number of nodes is no more than n. It's n over 2 again, but okay, I just say n. I will get rid of all constants, which is not important. Yeah. So again, here you do n operations here, then go back, do n operations here, go back, and so on. And number of times you increase the matching again is n. So the total number for all these operations is no more than n squared. So total time complexity will be following. So n times we increase the matching. Each time before we increase the matching, we make all these contractions, so we have no more than n squared operations. And every operation is actually DFS or something else, which works in linear time. So it works in linear time. So that's the total complexity of this algorithm. Interesting question is, can you do it faster or not? Is actually answer is you can, but it is complicated. We have enough time. Yeah, we have some time. So if you will try to implement this algorithm, you can implement it just like this. So all steps here are actually quite clear. So for every step, you actually know what to do. There will be a lot of code, especially when you try to expand back your blossom and so on. So there may be some complications, but it's actually doable, right? But you can make even faster algorithm, and it actually will. It's easier to implement. You can do it like this. What can I? Let's write this. Yeah, let's write this. You can actually do it all in the same DFS, like we did in the Kuhn algorithm. So in the Kuhn algorithm, we need to find augmenting path, then find it, and then when invert this path. And in the previous lecture, we did it in the same DFS. Here we can do kind of the same thing. We can run Dfs algorithm, and this Dfs will find the augmenting path, will contract all the blossoms, will invert the path, and so on. We'll do all the stuff in this single DFS. So you do it like this. So what happens? You start DFS from some free node. And run the DFS algorithm. So you start from here, you go here, then go here. Let's stop here. So you visit this node in state 0, 1, 0, 1, 0. And here you find this edge, for example. So you find this edge and you find the blossom. Again, what will happen? You have your DFS algorithm. This is your current node V. You iterate through all possible edges from this node V. If you have edge to some node U, which is not visited yet, so you simply recursively call DFS from here and mark is the state 1. So you mark the state 1, run DFS from here. If you visit some node which is already visited with state 1, then you just don't go here, and just continue, because you already visited this node in state 1. So you visit everything possible in the state 1. So you just skip this node. Now, if you find the edge to some another node U with state 0, it means you have a blossom here. So again, this is your current state of your DFS algorithm. You're standing here in the state 0, and you find edge to another node with state 0. Then you know you find the blossom. What you can do? This blossom is always contains some top nodes from the stack of your recursive DFS. Okay? So this is the stack of your recursion. So you start DFS from here, then go here, then go here, go here. So these nodes are the top nodes in the stack of your recursive DFS. So what you can do, you just take these nodes from the stack of your DFS and then contract this blossom. So just So you just remove all these nodes and replace them with one big node. Now what happens? Now again, you have your graph G prime, and you need to run DFS in graph G prime, but your current state is already a valid state of DFS in graph G prime. So you just say that this is your current node. So again, you imagine you start DFS in graph G prime. So you start DFS from here and then go here, here. So this big node is the current node of your DFS in graph G prime. So you can just continue DFS from this point. Yeah. So just contract this blossom and continue DFS from here. So you just take this big node and continue your DFS from here. So you take the next edge here, then take edges, and so on. Now, if your DFS will return true, so if this DFS actually will find some augmenting path, then when you go back from the recursion, you actually invert this augmenting path. So when you return from the recursion, so again, you start from here, go to here, and then continue here. So when you go back from the recursion, you invert this part of the path, and now you need to expand back your blossom and continue the recursion. So you expand your blossom, add all these nodes to choose the side of your path, add this part to your to your augmenting path, and then go back to recursion here. Yes. When you conduct the interesting thing that you actually have some nodes going from here. So when you construct this blossom, you need to merge all the adjacency list of all these nodes. Yeah. So you need to take all the adjacency list of these nodes and combine them into one. Combine into single list of adjacency list for this big node. Yes, true. You can do it. You can concatenate different. If you maintain these lists as a double connected list, for example, you can concatenate all these lists in linear time. Linear by the number of nodes here. So the time you need to spend contracting this node is linear of the size of this blossom. And the number of nodes you remove from your graph is actually linear of the size of this blossom. So again, if you have the blossom of size k, then you have linear time to contract blossom. It's actually not. It's actually not. Let's say like this. It's actually not linear, but close enough. So you contract. So if you can contract the blossom of size k in linear time, then you spend this time to contract this node, and the number of nodes will be n minus k plus 1. Yeah? So you decrease the number of nodes by k and spend k time doing this. Now if you take sum of all these elements, so if you have k1, k2, k3, and so on, I need another letter, p. Yeah. Then the time I spend is sum of ki. Yeah. And if you look at this thing, that each time I decrease, so I take n minus k1 plus 1 minus k2 plus 1, and so on, must be at least actually 1, but it doesn't matter. So if I remove this to the right, this to the left, then sum of all k's will be no more than n plus number of these ones plus p. So time complexity is actually n plus p. Then p is the number of times I need to contract the blossoms. Yeah, so p is no more than n. So this is the O of n. Yeah. So actually the time you need to contract all this blossom is actually linear. Why not exactly? Because you actually need something like union finite structure. You kind of need to maintain the current sets contracted, yeah? So for each node, you need to know which blossom it actually belongs to. Well, because when you go here, so at some point you may have edge from here to here, something like that. You may find edge like this. And you need to know that this edge actually goes to this node, and this node belongs to this contracted set. Okay? So for each node, you need to find the set containing this node. So you need to union find the structure for this. You can avoid this, but it's complicated. So we will not do this. So actually, this is not linear, but linear multiplied by inverse Ackermann function. Not a big deal, but yeah. Finally, what people can do, people know how to do it in time. So the best time known to solve this problem is actually, maybe, I believe it's the best time known, is square root of n multiplied by m. Okay, this thing is kind of complicated. We will find the algorithm with this time complexity for bipartite graphs. So we will talk about Hopcroft-Karp algorithm for bipartite graphs with this time complexity. It can be generalized for non-bipartite graphs to make non-bipartite matchings in this time complexity, but it is really complicated. So not this year. Maybe at some point we'll talk about this, but no. So it's possible to find non-bipartite matchings with this time complexity, but it's much more sophisticated algorithm to do this. Usually, so if you just apply this, then okay, let's update this. So if we do it like this, then we actually do all this thing can be done in linear time. Yeah. So total time complexity will be something like that. Maybe multiplied by inverse Ackermann function, doesn't matter. But yeah, this is actually good enough, usually. For small graphs, usually you don't want to find matching for big graphs. If you actually need to find, usually it's actually faster. If you just start your graph from some greedy algorithm, so you just greedily take some edges, you will find almost maximal matching. So a lot of heuristics which actually helps, but okay. Any more questions? What the state of proposed? What will be the state of proposed node? State will be 0, of course, yeah. Because this is the node compressed from this node, so we go from here to here, so the state will be 0, yeah. So we contract all these nodes in the single node and start from here, the state of this node is 0, yeah. So the next edge must be not in the matching. Yes, yeah. So this optimization actually removes all this stuff with a single DFS, basically. So it's a single long DFS. So DFS goes, sometimes it contracts some sets, sometimes it goes here and so on. But the total complexity will be linear, yeah. So you spend m time for the whole this puzzle. So this part is actually n plus m. And you do it n times. So n plus m multiplied by m. If m is greater than n, I always assume n is greater than m. M is greater than n. So number of edges is greater than number of nodes. If the number of edges is less than number of nodes, then the graph is not connected. So you can just split it into components. Okay. Hope it's clear enough. This is one of the most complicated algorithms for this semester. So if you didn't understand some parts of this, that's okay. So there are a lot of small details. If you try to implement this, you will find a lot of small details. Good luck, actually. If you try to implement this, it's a good exercise, but so it's usually, yeah, it's hard to do it from the first try, but okay. So that's all. Yeah.